makes it easier for us to handle the masses of data that we keep acquiring. So I'm very much looking forward to this. I introduce John and Rob, who told me to tell you that they are both nuts and that they've been working on this for over 5 years. So we're lucky to have the results of real research.
Hi, Scott.
Please welcome the speakers.
Hello.
Rob, you want to tell about yourself first?
Yeah, so I've been in systems engineering field since 1988. Who here is older than that? Whose birthday? Okay, 3 of you got, 4 of you got. Okay, great. So, really?
We're holding up pretty well for old guys.
I know. So I got into the field in the ripe old age of 18. Kind of figured out what I wanted to do very young in age. An uncle handed me an old Apple computer and said, hey, you can do anything you want with this. And I said, what do you mean? He said, think of it like a box of Legos. If you can build with Legos, you can build any kind of software that you want. I took that to heart. Fast forward, where I'm at now. I have an exciting opportunity to do some really cool stuff for a really cool employer. And met John about 5 years ago. And we've been doing some crazy things ever since. John?
Yep. So I'm a quant. Originally trained as an economist. I really like solving puzzles and crunching numbers. And so what I've actually realized in the last couple of years is that means I'm called a data scientist. But
what is that, John? What is a data scientist?
Data scientist is a cool term for a statistician. So anyway, I like playing with numbers. It's really fun because you go to parties and you tell people you do math, and the first thing they say is, I hated math in high school, and they walk away. It's actually really awesome if you don't want to talk to somebody.
John is the awesomest wingman ever.
So yes, and we have a lot of fun because Rob knows how all the networking stuff works, and then I say, okay, how do I represent this with numbers?
Yeah.
So we are the two great tastes that go great together. And as Rob mentioned, we started working on this about 5 years ago.
Yep.
And the story Rob likes to tell is the first time we met,
so
Rob's...
I'll take it, John. So John, I said to John, hey, John, I want to talk to you about the data sets we're going to be using. He's like, no, I don't want to know anything about them. I'm like, what do you mean? First guy I've ever met, first data scientist I ever met, first. Usually database administrators are like, you got to describe all your data to me. What are you talking about? What is this data? How do you organize it? John was the first guy I ever met that said, don't tell me anything about your data at all. I'll figure it out. I was like, cool. What's your background? He's like, medical. I was like, here we go. So the first thing I sent a data set over to John. He runs it through some analytics. He comes back to me and says, hey, Rob, all these source ports are different, and they're talking to the same destination port in this data set that you sent me. And they're talking to this port number 80. What does that mean? I was like, well, John, they're talking, web traffic. And he's like, but why are the source ports all different? I'm like, there's these things called RFCs. And talk about the RFC comment that we talked about the other day.
The internet is a draft.
Yeah. So John says to me, he's like, where's the specification on these protocols? And I said, what do you mean? I was like, the RFC? He's like, no. After the RFC, there's this thing called a standard. And I said, we don't have those.
Right. And this is actually why I like the problem from a math and analytics and stats side, because usually when you're doing stats problems or math problems, you have a very clearly defined thing, you have very clearly defined structure, you have very clearly defined outcome, right? And you do your work, you do your proof, you collect your data, and it all sort of just comes together, and then you publish a really boring paper that nobody ever reads. And instead, here we are, and Rob's like, yeah, we don't have any outcomes. I'm like, okay, that's kind of an interesting problem. How do we find the unknown unknown? And that's kind of the theme of the talk, is what we've been working on for 5 years is munching on data and taking network traffic and finding ways to describe it to try and identify patterns or events without actually knowing what we're looking for.
We should probably click to the next slide.
Yeah, I think we probably should.
So it's enough about us.
Yeah, exactly. So why do we keep trying? Because it's a fun problem. So this is really important.
So John and I like to fail a lot. We do pretty much everything to the point of failure and come back out of the rabbit holes and figure out, like, what the heck did we do wrong? What can we do different? What approaches didn't we try? But it's fun to fail. Just remember that.
And actually, failing is important because that's how you learn.
That's right.
So a little bit of the background of sort of where we came from. So if you were here in 2014, Rob and I had built a game where you could visualize network traffic, and we did that in partnership with our employers at the time. We demoed that. It was very cool. It didn't really scale very well, and we were kind of struggling again with how to put useful information into that visualization that helped you make better decisions. And prior to that, the way we actually met was a client who wanted us to apply machine learning to network traffic. And so actually my background for a long time was I had started a machine learning company. If you don't know what machine learning is, the colloquial term for it's AI. But basically building software that allows computers to learn from data and from their environment. And when we applied machine learning to network traffic, what we learned was there are a lot of proprietary tools that make development really difficult. It didn't scale very well, right? That's actually one of the things about most machine learning software. It doesn't scale very well. And the result that we came out with wasn't really intuitive to someone who didn't have a stats background, right? So we produced stuff and it worked, but people didn't really know what the heck it said.
So the other thing was the customer said to us, oh, by the way, we're not parking the data. So you're going to have to operate on this data in transit, in streams, and oh, by the way, think of the largest data flows you can think of and multiply it by 10. So not only do we have to figure out how we're going to do this for real, but then also figure out how to make it massively scalable. And the tools at the time, we're talking 5 years ago now?
Yes, 5 years ago.
They were a joke. You either had to pay a 3-letter company that doesn't do Windows a whole lot of money for a whole lot of licenses for things, or you had to go real kind of cutting edge FOSS stuff with some stuff that was not mature at all.
Or you had to kludge Java desktop software, which really doesn't work at terabyte scale. And so the other thing that Robin mentioned, and we'll come back to this in a few slides, if you're going to use machine learning or statistical software, right, that stuff usually requires you to assemble a lot of data to train the algorithm. And so one of the things we've been trying to get away from, you can never get away from training, but we're trying to figure out how to minimize the training burden, right? Because when you're dealing not only with big data, but, I said big data. Not only when you're dealing with large volumes of data, but when you have a system that changes a lot, right, building a training set is very, very difficult. So, all right, failing like a boss. Actually, I stuck a little thing down here in the bottom right-hand corner. That's my whiskey ontology.
So John and I like to draw on whiteboards a lot.
Yes.
And the only way we can capture any thoughts that we have, because each of us races really fast, is kind of phone capture, the whiteboards, and but bottom line is, if you're going to fail hard, because when you fail hard, that's a great stopping point. Don't go any further than that failure. Don't try to figure out like, oh shit, I failed. I'm sorry. Just fail hard, stop, and then know that that's an endpoint that you don't ever need to go to again, barring like largest changes in technology or something coming up that you just don't know about right now. I think you can get dumber if you try.
Yeah, so I think starting out with this like apply machine learning algorithms to large volumes of streaming network data, what are some lessons we took away as we've continued to play with this idea? And the first one is keep it simple, right? And don't over-engineer your solution. You can fall in love with the beauty of the math and the analytics and the algorithms. I've done it. What you'll find out if you actually do this enough is that the more sophisticated and beautiful your analytic, the more headaches you have, and it doesn't actually necessarily give you a better result.
Now try to put that in stream, okay? So now take that beautiful analytic that John spent all this time on, looking at sets of data at rest, and then try to put it into a stream and wonder why it bricks machines.
Right. So how do you scale it, right? You got to scale it. And then the other thing is, you can get dumber if you try, right? And a quote that I actually love is Antoine de Saint-Exupéry, who wrote The Little Prince, and I'm going to paraphrase this wrong, but he basically says, perfection is when there's nothing left to take away, not when there's nothing left to add. So what we focused on is how do we kind of pare this away?
Oh, don't get off that slide.
Yeah.
So the last bullet point there is something really important. We're looking for help, right?
Yes.
You know, one of the things that we're trying to get to is not you know, the Rob and John show, failing at shit for 5 years, the same way, different ways, whatever, coming up here every couple years when we get accepted to ShmooCon and showing you another dumb visualization. We need help. So we're going to talk about that a little bit later, about how we're going to solicit for your help. But keep that in mind. Like, if you've got some crazy great ideas that you're willing to try, you know, come hit us up later, okay? And we'll give you some contact information. But we're going to ask you some questions.
So our idea was, how do we boil it down even more? How do we make it easier for people to understand? We basically boil it down to 4 key pieces, right? So sensing data. So we'll talk a little bit about sensing and sensors. Ingesting the data. So once you sense the data, you have to collect it somewhere. You have to do some basic preparation to do operations on it. Enriching the data. So this is where sort of the analytics piece comes in, but we're trying to keep it really, really simple. And then visualizing the data. So how do you provide scalable visualizations that anybody can look at and at least get something out of, even if they don't know the specifics of the network and they don't have the engineering background? So how far did we make it?
Not far enough. So right now, we kind of are using for sensors a very old kind of library that's been out there, called SoftFlowD. It's kind of wrapped into a bunch of different open source routers, like pfSense, OpenSense. It's been around for a long time. So we took a fork of that and put it onto some hardware, so we're able to actually run and generate NetFlow flows. So we're kind of confident that we're pulling some interesting data. We try to stay away from PCAP because when we get down to the PCAP level, we found we fail really fast, really hard. It just is, you know, not something that we can do reliably. There are some hardware options out there that are interesting, that are coming out, that we might be able to do some full-blown PCAP with.
Yeah, your scaling problem gets worse, and the other problem is, from an analytics perspective, when you get down to the PCAP level,
Right.
Even though the syntax is consistent, the structure of the data is not.
And
right? And analytics need structured data in some way.
John keeps telling me that all the time.
Yeah.
So we decided to go with aggregate flows at the NetFlow V5 level, since that was kind of like the easiest way to do network sensing. The ingest, John and I talked about it. We've been playing with streaming analytics for a long time, and we're talking about true streams. We're not talking about stuff like Spark. We're not talking to stuff, you know, where micro batches or parking data, or running jobs where you got a gigantic Hadoop cluster and you're pulling data off the cluster and analyzing it and creating analytic results and then pumping that into visualization. We're talking about actually taking the data off the wire, running it through analytics, and then producing the visualization without parking the data at all. We do a lot, and pretty much everything that we're doing is open source. The tools that we're using to enrich data are all FOSS tools, toolkits, and stuff like that.
Stuff like SciPy and
SciPy, R,
Weka.
Yeah, all the pandas. I mean, there's a million toolkits out there.
As an analytics guy, what I will say, I mean, it's my considered view that before you build any analytic or any algorithm, you need to go hit some of the public libraries. Because there are so many analytics out there, I just cannot imagine that if you need to build your own algorithm, like special customized algorithm for analyzing your data, you either have a really weird problem or you haven't done your homework. Because there are so many libraries out there for this stuff that are so easy to use. Anyway.
And I don't do math, so for me it's easier to get a toolkit. The visualization, we started off with like force-directed graphs, and I don't know if any of you guys were at ShmooCon 4 or 5 years ago, where I did a big Twitter hairball with a really smart guy who invented some force-directed graphing and 3D visualization in JavaScript. We were the guys that had the Twitter cannon that was firing off hockey pucks. So that was kind of our first jump into it. We played around with a bunch of game engines. A couple guys came through a couple years ago and told us that our game engine sucked. I don't see him in the audience. So,
but it was kind of
Jedi
sucky.
here. Anyway, So we decided that we were going to take a look at some really good, game engines that could actually scale. Looked at the Unreal Engine, and that's kind of like where we're kind of stuck right now, is looking at what can we do to keep these visualizations faster. So, John? I'm sorry, the computer vision piece.
Oh,
Let's
yeah.
back up first. On the computer vision aspects, we realized that we needed another layer of taking our analytic results and analyzing them ahead of time. And one of the things that I love is, as a hobby, is robotics. And I've been playing around with the robot operating system for a long time. And one of the aspects in there is the Open Computer Vision project. And so OpenCV has a lot of really cool algorithms in it that allow you to analyze frames of information. And has anybody seen the video where the guy taught the Super Mario Brothers to play itself? Okay? All right, good. So he was taking slices of memory, right? And what he was doing is he's analyzing each frame of data. He was pulling from the frame buffer and taking a look at each frame and saying, is my score going up? Is my score going down? What kind of information can I glean from this frame of data? So I thought to myself, I was like, shit, if I took our analytics, compressed them down into something that the computer could recognize as a frame and analyze previous frames and take lessons from that and going forward, what kind of information could I glean? So I'm not there at the bottom yet, but I got the data that can go into that kind of thing. So all right, John.
Right. Cool. That's all right. So crazy problems for crazy people. This is where I talk a little about math and data science and stuff. And so, as I'd mentioned, one of the challenges that we've had, right, which actually has been part of the reason the project's fun, is that understanding network traffic is a very, very hard problem from a math perspective, an analytics perspective, a statistics perspective. What you have is a highly polymorphic system that's subject to emergent behavior. Does everybody here know what the word polymorphic means? Because if not, I'll provide a quick definition. It changes a lot and in very unpredictable ways, right? So the internet is actually almost like a living organism in that it mutates, it changes, it has its own behavior, right? And actually, if you want some really cool reading, just Google the term emergent behavior and go read about it, right? This is one of the debates around self-driving cars, right? Because the cars are autonomous and may start to behave in collective ways that we as people can't anticipate. What's interesting is that this is part of the reason we have financial crises, right? All of a sudden, everything's going great, and then the stock market drops 1,000 points, and all these people are sitting around having lost tens of billions of dollars and scratching their heads being like, oh, I didn't see that coming. Well, right, because it's a highly polymorphic system with emergent behavior, and things just start to happen. And the challenge is that if you think about classical statistics and analytics, right, I have a defined outcome, I have a defined starting point, I have a very defined system. Okay, sports analytics and sports statistics are really awesome and fun to play with, and they're great for teaching because they're really consistent. It is really, really, really unlikely. The probability is not zero, but it's really small that next year someone is going to hit 95,000 home runs, right? I mean, it could happen, but it's really unlikely. On the other hand, in things like financial markets, the internet, certain different types of systems, of which networking and financial markets are the two really good examples. Tomorrow someone shows up and hits 95,000 home runs and you have no idea what just happened, right? So it's a really challenging problem. And if you really, want to get into it, this goes back to the beginning of the project where we were trying to solve this using Bayesian networks. I don't know if you know what a Bayesian network is, raise your hand. Right? Okay, so some of you... So
they don't work. They don't work.
No, they work. They work fine for what they're designed for, but they're conditional. They're graphs of conditional probability. So if I know these two things, here's the likelihood of something else happening. Right? So if I have a network with 3 nodes, the state of node A is conditioned on what I know about nodes B and C, right? Which sounds simple enough in its own right. But then you realize that nodes B and C have all these different potential states they could be in. So if all we're doing is trying to model port pairing, right, I have 65,000 squared states that any pair of nodes could be in. And the state of node A is conditioned on those 65,000 squared states of nodes B and C. And very quickly this becomes what's called an NP-hard problem. Right? This is not a problem you can simply compute. And so people usually go at this problem with heuristics. It works great if you have something that is reasonably stable, like genetic data, right? Because there are genetic mutations, but they don't happen super fast, right? Again, evolution moves along, but it doesn't move that fast. The problem is that evolution in networking data is crazy. It happens lightning fast. So we said, okay, how do we try to get at this? And we realized that the challenge is not how do I make a computer function like a human. We've been trying to do this for a long time. We have much better autonomous systems. But as someone who's an old machine learning guy, I actually have come to the conclusion that trying to create strong AI, trying to make a computer behave like a human, is not a very productive exercise. In fact, what we want to try and do is make the computer dumber to make the human smarter, right? So how can we actually use the analytics and the visualizations to try and push lots of data at a person in a way that a person can understand? If you think about it, evolution has engineered us to be able to detect things really, really fast. That's why we don't get eaten by tigers, right? I mean, I'm sure some people, well, we've probably seen them in the zoo. There are probably very few people in this room who have actually been in the jungle and bumped into a tiger. But you know enough to know that if you see one, you probably walk the other way, right? Teaching a computer to do that takes a shitload of data, right? So the question is, how can I use the computer to provide the data to you in a way that makes sense and let your brain do what it does really well, which is sparse pattern recognition? So this is actually a picture of a rug in my house, right? And the point I make about the rug is you can look at this rug and you can see the pattern and it totally makes sense. If I showed you the loom or the weaver working with all the threads, it would make no sense to you. So how do I turn the threads into a pattern you can get? This other slide, which I know Rob is sick of seeing because I love it so much.
So can I talk to this one?
Yes.
So what do those three top things have in common? Anyone know? Anyone? They're birds. How do you know that? You're fantastic. You're smarter than a computer is already. So if we look at the bottom row there, what do we see? Well, if you look to the very end, you'll see a school bus and a CAPTCHA, right? You guys know that. But what the actual computer sees is a bunch of nonsense that it can't recognize. Unless you do really extensive training, then it's only good 2% of the time. Okay? That's the reason why CAPTCHA is CAPTCHA. Because if you can define and build up a really good CAPTCHA breaking system, then you're probably going to get some phone calls from some people that offer you a lot of money. But anyway, the point is that you can tell a kid, hey, this is an eagle, this is a bird. This is a swan. This is a bird. And even though they don't know what that third one is, a cardinal, they'll look at that and say, that's a bird. And that's actually kind of interesting because all you had to do is provide a training set to a human that was 2 instances deep, and they kind of get and grasp what that is. Okay? John will tell you about all the points and vectors and all kinds of other math stuff that would have to go into training a computer to do the same thing. And we can do that pretty quickly, right? So that's kind of where we can actually outpace a computer with pattern recognition.
You got it.
Good.
So the answer is keep it simple, stupid, right? How do we boil it down and use simple data, simple analytics, and learn from smart people? And these are two really awesome talks. So we also have a bunch of different things that we've looked at and seen that have kind of inspired our work. And one of these, I'll let you talk about Chris Domas.
So anybody know Chris Domas? No? Yeah? All right. See a couple heads shaking, a couple people talking. All right, great. So I don't know how I happened on it, but he had this thing about, I think it was ones and zeros of cyber defense. Don't throw a ball at me for saying cyber. It's his title, his talk. But basically what it was he was taking an OS and representing the ones and zeros in a three-dimensional cube, and then looking at how malware was applied to that and slicing and dicing it all different kinds of ways. Go check that talk out because that was really inspirational and gave John and I a whole bunch of new inspiration to go figure stuff out. And then Jeff Jonas, he tortured his family. I don't know if you know who he is, but he does a lot of context-based analytic stuff, right? And so what he did was at Thanksgiving, he took 4 different puzzles and mixed them all together and took pieces out and gave them to the kids at Thanksgiving and said, put the puzzles together. And then every 15
pieces
minutes he
out.
would come in, he would do a timeline of what happened when, and eventually the kids figured out that Uncle Jeff was evil, and had pulled pieces out of the puzzle, had mixed puzzles together, and kids couldn't figure out what to do. But they had the context. They had enough of the puzzle to figure out what the thing actually was. So that's kind of two things that kind of triggered John on to our next step. So.
And actually, has anybody here ever had a chance to hear Jeff Jonas speak? Yeah, okay, a couple of y'all. If you ever do it. I mean, in my view, it's the closest thing I've ever had to a religious experience. The guy is brilliant. He's the fellow who busted the MIT blackjack team. And a lot of his work with the matching the pieces is around some work he's doing called space-time boxing, where he basically threw out this idea that, hey, we don't actually have to fit everything together perfectly. You just have to get it close enough. And so he's actually, one of the things he's doing, which is really cool, is he's helping NASA with the asteroid problem, right? The asteroid problem being that at some point if a large asteroid hits Earth, we're all extinct, so we better figure out if that's going to happen and take some action.
It's happening next week.
Right. So actually, NASA couldn't make any headway because they're like, well, we have to compute all these trajectories all at the same time, and there isn't enough compute power. And Jeff's like, no, you just have to know if two asteroids are going to be close enough, and then compute those trajectories. And they're like, oh, yeah, we hadn't thought of that. So where are we now? This is an old joke that I like. So
your joke, John.
This woman's up in a balloon and she gets lost, and she sees this man down on the ground. And she says, do you know where I am? And he says, yes, you're up in a balloon. And she says, you must be a senior manager. And he says, I am. How do you know that? Because you just told me something that's totally correct and absolutely useless. So we're trying to get away from doing stuff that's totally correct and absolutely useless and getting more to stuff that's like 98% correct and more useful.
Or just wrong, so we can learn from it.
Right.
Okay, where's the cheese? So, does anybody recognize this image? Yeah? Yeah, some big fans out there. All right, cool. Anybody know what that information in that graphic is plotted on? How does that plot work? Not my coworkers. So unless you really take a look at this and really understand how this plot works, what you'll notice is it's the actual top-level domain plots, okay, of the entire internet range. And the way it's plotted is on a space filling curve. Okay, specifically a Hilbert curve. Go ahead, John, hit next. That actually looks like that underneath, okay? So what's pretty cool about this plot? It takes information that is in 1D, okay, in one dimension, and allows you to plot it into 2 dimensions, and keeping the closeness of the values of the data, all right? So the majority of the time that when we're dealing with information, when we're doing an analytic, the analytic result sometimes comes out in a single value. And what we want to do is we want to plot it. And if we're looking at a network, for example, if I'm looking at the lowest level of the network on the WAC 24, I've got 255 IP addresses, 256 that I can actually plot. I can take that information and plot it onto this graph pretty interestingly, and I'll show the closeness. Now, why is that important? Well, I don't know about you. Some network administrators I know like to have a DHCP range. They like to have a static range. They like to have a range of addresses that they put certain piece of equipment in. Okay? Well, that person is thinking in their brain, I'm going to put these things together. I want to put these things together. I want to put this together. Okay? If you plot the data on a space filling curve, you'll actually see that information into centers of information that you can decipher later. Okay? Now, who here could write a function that would produce that graph? Without cheating, without Google. Without Google. All right, so John hit it. Okay, so I did, and if you look at my exception down there, it caused me a lot of pain and consternation to get right. Because I know absolutely nothing about math. And I had to take some code that somebody else wrote, convert it into Python so that I could actually run some tests and see if it actually worked, right? I left out the rotation function, but all this code is going to be up on the GitHub later anyway, so you can all have it. But it was kind of interesting because, I had never really played around with this kind of stuff and plotting and taking a single value and plotting it at X, Y. So it was kind of interesting to play with. Okay, hit it. Right now, where we are as far as the how we do what we do, we're collecting and sensing and generating net flow traffic. We're ingesting that into a streaming platform called StreamParse, which runs on top of Storm. I'm not sure if you're familiar with StreamParse, but basically what it did was it took and actually allowed you to do apply different languages to Storm. I don't know.
Right.
Anybody in here a Java fan? No? One Java fan? Josh? Just who's? Yeah, I know, but it's just Josh. Josh don't like Java anymore.
Who's familiar with Apache Storm in here?
Apache Storm.
So Storm is a very cool streaming data environment, right? It was built by the same guys who built Twitter. Right. It's basically the backplane for Twitter syndication. So it's a very powerful streaming data environment. But as Rob mentioned, the challenge is it's all Java native.
Right.
And so there are analytics in Java, but then you get back to the problem we had with the machine learning stuff, which is when you're doing lots of machine learning and training and analytics, the Java doesn't scale very well.
Well,
Python
the problem that we have is guys like John have been working in R and working in Python. And they throw the code over the fence and they say, hey, Rob, this is the code that I want to implement. And I'm like, okay, so now I got to go from R Python into Java. This sucks. So luckily, a guy named Andrew Moltalenti at Parsley created this thing called StreamParse. Even though Storm was supposed to be multi-language, it wasn't out of the box. So Andrew made it happen by taking a closure wrapper and basically allow you to implement spouts and bolts into any language that you want just by providing the topology via closure. Again, that's a lot of boring stuff unless you guys are really into it. Anyway, so that's kind of what you see down there. We can implement custom algorithms and any free open source out of the box algorithms that are out there to ingest and enrich the data. Right. And then the visualization piece, what we're trying to do is we're trying to compress down the analytic results into really small things. We can get about 1,024 analytic results in a 16 by 16 pixel image. That seems crazy, but that actually covers your entire network. So we're taking...
and it would run on a mobile phone.
So we're taking a single pixel and in the RGBA channel, okay, so 4 channels of color. I can take 4 analytics that kind of John decides are interesting to put together, take that, colorize a pixel, plot that on a Hilbert curve, and in 16 by 16 pixels, get you 1,024 analytic results on your network, on a WAC 24.
Which is a perfect segue
into
how we're getting those channel values. So first of all, a PSA. For every line of code we write, we're donating $1 to the prevention of statistical abuse.
Because we abuse statistics a lot.
Yes, because we're basically grabbing stats functions and using them for things they weren't designed for. So the way we're getting the channels right now to make it really easy and simple and reuse stuff is the SciPy library has lots of math and stats functions, so it's really awesome. And Rob and I were talking on the phone just before the holiday in early December, and we're talking about how to describe this data, right? And again, the problem is no outcome, right? No outcome, and because it's streaming, it's floating, so I don't have my usual, here's a year's worth of data to train your analytic on. I said, so I need to be able to boil down changes in state of this node to a simple number with maybe a handful of observations, right? And I have to do this very quickly over and over again.
So we're running the sample. So in a stream, you have a window that you have to operate in, okay? So you have a sliding window that constantly moves, and the information that you maintain, and these are the hard problems, right, with running analytics in streams. It's what is the size of my window? What makes sense? How do I apply the analytics? What do I have to hold? What can I throw away? What TTL's off? And you got to think about it in just a moving environment, right? So it's actually like you watching traffic patterns before you cross the street or make a right turn, a left turn in traffic. You really got to have a sense of your surroundings and only house what information you need at that point in time to make a decision, right? I mean, it sounds simple because we all do it every day.
So when you're crossing the street, you're not really thinking about what's going on with the French government, right? You've got exactly what you need for the time period you need it.
Exactly.
And so sitting, in my car in traffic, I was thinking about this, and I realized all we need to do is describe the shape of the distribution, right? So think back, if you guys haven't done stats recently, think back to your college stats class, right? You do that little histogram plot where you count, like this is how many basketball players I have, and you plot it out. And I said, all we have to be able to do is reduce the shape of that distribution to a number. And the beauty of this is that there are lots of stats functions for doing that. The ones we picked were skewness and kurtosis. Skewness basically says, which way does my distribution lean? And kurtosis tells me how spiked it is, right? So a high kurtosis, if I have a distribution of destination ports with a high kurtosis, it basically is pointing to like 1 or 2 ports, right? If I have a kurtosis value of asymptotic 0, it's telling me that I'm talking to everybody. Now, the reason I put in the prevent statistical abuse slide is
because I said, John, just give me a color.
Yeah.
Just give me a color of my
you
pixel. Just color my pixel.
who are statisticians, you're going to raise your hand and be like, that's not what these things were designed for. And I'm like, yes, you were correct. That is not what they were designed for. We're hacking stats.
Stats, right.
They were designed to compare populations so you could test the difference. And we're going to get there eventually, but for now, we're basically hacking them because it can reduce a distribution to a number. And in order to do the alpha RGB channels, we need a normalized number between 0 and 255.
Okay, so apologizing ahead of time for all your statisticians.
Yeah, and that's why the rocket bike's on here, because you weren't meant to put rockets on a bicycle.
Don't put a pulse jet on a bike.
Yeah. Because you'd have too much fun.
Right. Oh, wow. All right, then.
All right. So we're back to,
Okay,
we're
so,
here to our video.
Okay.
5 quadrants.
5 quadrants, apparently. So you're going to see a video, and I'm going to describe it. Yes, it is.
Yes, it is redundant, yes.
But it makes sense to me. So, and I suck at math.
We were working on this, and we're like, oh, we have quadrants. Oh, wait a minute, that's 4, and we have 5.
We have 5 quadrants. It was worse before.
It's a quadrant, right.
So we're going to show you an image up here, an image up here, an image in the middle, and 2 images on the bottom, okay? So you're going to see 5 images that are plotted in the Hilbert Space Filling Curve. Each pixel that you see on there is representing 4 analytic results.
Right, alpha RGB.
Alpha RGB. John has a really, really highly technical, we were going to hand this out to let you decipher what, but I said, John, it's 10 o'clock on Sunday after the Saturday party. Tell you what, why don't we just ask them to watch the video and remember which one they thought was interesting, and then when the video's done, we'll ask the audience to raise their hand and which one they thought was interesting, and then we'll tell them what it was.
Even though I do have a friend who's going to make this into a quilt.
So what I'd like you to do is just tell me what area draws your eye, what is interesting to you, and then we'll tell you why. And then, just this population of people are going to tell us some really interesting things. And again, this is what we're trying to do is to get the interesting information from people, right?
Right.
Okay. All right, John, show the video.
All right.
Are you really going to turn it on?
I am going to turn the music on because it's cool.
Okay.
So. Yeah, I know it's a dorky joke, but.
Okay. So this is a 2-minute sample of network traffic that is running through, I think, about 14 analytics sliced 5 ways. It looks really boring, but there are some things in there that are changing, and there's some things in there that are interesting. And each plot has a different set of analytics that tell a different story.
Oh, that's right. I'm not allowed to talk about it.
There are things. There you go. Well, that's a great question. Is that interesting to you? Save that for later.
If it's not changing, it's because the distribution, the shape of the distribution, isn't changing. Yeah.
More interesting questions. So as you can see, we see some interesting things happening on the plot. There are some different colors there.
Yep.
The sample was taken over 2 minutes in live network traffic. We recorded it to just please the demo gods, but in reality what would happen is this output would then stream into a computer vision system that would allow us to create tips for information on what we need to look at based on the types of analytics that we're running in the quadrants. What does darker or lighter represent? Okay, so I'll tell you what. I'm going to let John get through. Did you hit pause? Just hit pause.
All right.
All right. And I'll tell you what. Why don't you talk to
What this stuff is?
What this stuff is.
Yeah. So the answer, Mouse, is it depends on the plot. So sort of colloquially, we sort of name the plots. The upper left-hand plot is data spewing. So basically, we have 4 channels. The alpha channel for all of these is the amount of outbound traffic. So how active the node is outbound. So the opacity of the color, right, is outbound traffic. The blue channel is high inbound traffic, right? So if stuff tends towards a blue or a darker color, it's an inbound. It has a lot of inbound traffic. It's consuming a lot of traffic. So for example, some of these nodes that are sort of gray, right, that become black, some of the ones that look purple, these are nodes that are consuming a lot of traffic. So those are consistent amongst all the plots. But upper left-hand corner is data spewing, which basically compares the source port and destination port byte spreads. So how much data am I sending from how many ports, and how much am I spreading that data amongst other machines, right? That's why I called it data spewing, because if I'm really highly focused, so if it's like a rich red or a rich yellow, I'm actually very targeted at one machine. On the other hand, if it's like a green or a light blue or a pink, it's sort of spread out. The upper right hand is how big are my bytes, and basically that looks at the size of the packet size relative to the flow, because we're looking at net flows. The flows and the bytes are aggregated, right? But we can still calculate the total number of bytes relative to the number of conversations the machine is having. So basically, in this case, if I'm looking at, again, a nice, in this case it's different because the yellows are very focused, a small number of very large conversations. The reds and the blues and the purples are large conversations but pretty well spread out. The one in the middle is how many nodes are hitting me, and the one in the lower left is how many nodes am I hitting. And then the bottom right hand is promiscuity. So actually the yellow boxes in that one mean that I'm actually not very promiscuous. I'm actually a fairly monogamous machine. Whereas the darker boxes, and in fact there are some red ones that pop up as you run the video, the darker boxes and the red boxes are the machines that are talking to lots of different machines. And I think one of the things that we've been trying to get at with these is, with this really cool sort of 8-bit-esque visualization, we can show it to someone who's not necessarily an expert in network engineering or analytics and say, okay, point at the thing that lights up. And so when I first started looking at these, this cluster down here, right, it shows up in all the plots. So there's something, and those machines are actually, it's not bad because when you do the color key, you find that they're actually pretty consistent machines that are fairly monogamous. And so, it's either something bad that's been going on for a really long time or they're doing what they're supposed to be doing. But as I run the...
so hold on, just make a comment about that.
Yeah.
Knowing where I sampled this data from and having played with this data set for a long time, I know that that deep cluster of machines on the bottom in the center is the infrastructure machine. So your
switches, routers.
Your Active Directory, your switches, your routers, your mail servers and stuff like that. So they're pretty consistent in their functions and what they do. And then the other machines are kind of scattered around throughout the plot. Some of them are in the DHCP range and some of them are other network machines.
But what's kind of fun, I know, on this video is when we get to around 29, 30 seconds, there's a node that sort of lights up in the middle and changes color really quickly, right? And then it sort of goes away, right? So this node sort of shows up, starts changing behaviors, and then goes away. And I actually don't know what the heck that node's doing. But part of the premise of this is that I don't have to, right? I can now say, okay, I need the IP address for this machine, and we need to go look at the machine and see what it's doing. Because everything else has kind of nice, consistent behavior. And this gets back to the point I made earlier, as an analytics guy, right, when Rob told me, well, we don't have any outcomes, after I sort of recovered from that, I'm like, okay, so we have to be looking for stuff. We have to be able to very quickly identify when you're changing your behavior, right? So it's not about saying, I know this is good or bad or this or that, but hey, this machine just showed up, changed its behavior, and went away, which may be legit, but now you know where to look. So I'll be quiet because we probably want more questions.
Okay, are we ready to roll in the next questions?
I think we're ready for questions because all we have now is the...
Let's put up the contact info.
Yeah. And of course, questions.
There we go. So any questions? Zach?
So you said in the top left corner was data stream. Just give a quick overview of what the other
Yeah, John, you want to? So the question was, what did a 4-quadrant or 5 quadrants mean?
Yes, so each quadrant. So the data spewing, basically, we're using a kurtosis metric, which is how peaked the distribution is, so how focused it is, and we're comparing the port-based byte outflows of the node to the destination ports that are receiving those bytes. And then we're adjusting that for how much inbound traffic is coming back to the machine. The upper right quadrant, we are comparing the bytes outbound from the machine to the conversations on the destination side, right? So subtly different. So one is the amount of data, the other is how many different conversations am I having. And we're also adjusting, in all of these cases, we're adjusting them for the amount of inbound traffic that's coming back. The center quadrant is basically looking at how concentrated my outbound data flows are, along with the balance of inbound versus outbound traffic, right? So am I mostly sending or receiving? The lower left quadrant is the same thing, except we're reversing. So in the center quadrant, it's biased towards inbound traffic. In the bottom left quadrant, it's biased towards outbound traffic. And then in the bottom right hand, we're doing the same idea of the kurtosis of the distribution relative to the number of IPs that I'm connecting to on my inbound and outbound flows. So e.g., how many machines, basically it's like taking all your friends and drawing a map of how much you're talking to your friends and then saying, okay, am I talking just to one person? So am I like a super duper introvert where there's like one person I talk to? Or am I like ultra extrovert and I'm talking to everybody? Oh, I think we're done. Thanks.
Thanks, guys.
I think we have some questions too, but
That's all right.